So we left off yesterday talking about drag force and terminal velocity. Terminal velocity, based on the equation we came up with, mg over b, because as time approaches infinity, that e to the negative bt over m term approaches 0. So then your velocity approaches mg over b. So then on the graph that we drew at the beginning, where we had the velocity, the object was falling and curving off like this. Well, this asymptote down here would be a value of mg over b based on the equation that we derived. Now, we left off with acceleration derivative. So if we take the derivative of our equation up here, derivative of the 1 is just 0. So then I've got mg over b, derivative of e to the something, in this case the negative bt over m, is e to the something. But then chain rule, you have to take the derivative of the something. Derivative of negative bt over m is a negative b over m. So then a of t, if we look at our variables here, let's see, b divides out, m divides out, and we get a is equal to g, negative g downward, e to the negative bt over m, which should make sense. It is a multiple of g. It is a multiple of 9.8. So then at a time of 0, our e is going to be 1, and so a of t will, or a of, not t, a of 0 will just be equal to negative g. A of infinity, our e to the negative b over t, bt over m term approaches 0, so then a approaches 0. So then you have a way to be able to model the acceleration and to model the velocity. We had talked about at the beginning of class yesterday as to what kind of a function that was for these. It's an exponential function approaching an asymptote. Now, this is one way to be able to model drag forces. We modeled it originally as that drag force was proportional to the velocity. Well, if you think about the curved part of the graph, we can also think of this as modeling that resistive force proportional to the square of the velocity. This application is much more limited, but it has its usefulness. I'm not driving an equation. I'm going to give you an equation. The resistive force is equal to 1/2 d rho a v squared. Let me fix my rho a little bit. Our different quantities. R, you know, that is the resistive or the drag force. D, that is a drag coefficient. It is the counterpart of the coefficient of friction, but for liquids and gases. Rho, RHO, Greek letter, that is the density of the fluid. In the case of air resistance, that would be the density of air. That's going to be a constant. So that would be a number you'd be given or you'd be able to look up. A is your cross-sectional area of your object. That cross-sectional area is in the direction the object is falling, or the area perpendicular to the direction that it's falling. And then your V is the velocity. If you look at this equation, you have a whole bunch of stuff you have to know, and it only really gives you a brief snapshot. If you know exactly what the drag coefficient is, what the density of the air is, what the cross-sectional area is, and you're looking at the velocity at a particular point in the fall, you can calculate a drag force. It doesn't give you a full-blown function for that drag force. It only gives you a value at a given time. If we have an object falling, mg resistive force, you can put this into net force equals ma and solve down for a terminal velocity. Gives you a little bit different function or a little bit different value, but it's another way of modeling it that is effective in certain circumstances. So 2 different ways to model it. Overall, AP is going to tend to use the exponential function more, but this will show up every once in a while in problem solving. Circular motion. We've already talked about centripetal acceleration. We also name that off as radial acceleration, and that is that center-directed acceleration, that turning or changing of direction that's acting on an object in circular motion, and that's v squared over r. Tangential acceleration, we've also already talked about. That's that linear acceleration when you have non-uniform motion and you have an object on a circular path that is speeding up or slowing down, and you're going to use motion equations to be able to typically calculate that. Centripetal force is merely the end result of when you put these things together with Newton's second law. Net force is equal to mass times acceleration. When you identify that this net force is center directed, the total of all the newtons are going to the side to a right angle to the object, then this A becomes an A sub C. So whenever you're drawing a free body diagram, F sub C is never going to go on the diagram. You're going to associate a centripetal force and a centripetal acceleration when you have your net force to the center. Okay, so it's a second name that's given to a center-directed force. So it could be friction in the case of a car turning a corner. It could be the gravitational force in the case of a satellite orbiting the Earth. So it's always a second name. Let's consider an example. Wonderfully dangerous, obnoxious ride. Swing out. Travels in a vertical circle. We want to sketch the forces acting in the right or at the top, the middle, and the bottom of the track, and then calculate other things. So here is our situation. We know wherever the object is, it's going to have weight. So I'm going to draw mg acting on the object at all 3 locations. Your object is going to be supported. It's going to have a normal force acting on it there. Okay, when it's on the side, it's not going to be in free fall because the motion is turning. And if the motion is turning, it's going to have a normal force. So I'm going to go normal bottom, normal side. At the very top, it will also have to have a normal force. Now at the top, that normal force in terms of a direction will depend on how fast the object is going. If you've been on a roller coaster loop before, if you are going through a loop very fast, then that normal force is pushing you inward. If you're going through a loop very slow, then you're hanging out of your seat, you're hanging into the harness on the seat, and that normal force is going up. So that normal force could be either up or down at the top of the path, really depending on the velocity of the object. So then we could draw it in either direction on our diagram. Part B, if the radius of the circular track is 25 feet, calculate the minimum speed that the ride must travel at the top to complete the circular path. If the object is traveling too fast, then your normal force is going to be downward. If your object is traveling too slow, then the normal force is going to be upward. If we want it to be just the right speed, then we're going to have no normal force at all. In other words, when we sum the forces at the top of the path equals ma, then all we would have would be mg, and that's equal to ma. Another way to think of it, If I had the ball on the string and I was swinging it in a vertical circle, if I'm swinging the ball too fast at the top of the path, I'm having to pull on the string. If I'm swinging it too slow, what's going to happen is the ball's never going to make it to the top of the path, but it's going to fall off and the string's going to go slack. So we'll never be able to complete the path. If I want the ball on the string to complete the path, it has to have a velocity at the top, moving enough so that the string is just at the point where it's not pulling inward, but the ball is not going too fast or too slow where the string either is pulling on or the ball is pulling on the string, or the ball falls in and collapses the circular path. So then you reach that minimum velocity when the weight is the only force causing the centripetal acceleration. So notice on my diagram, nowhere did I draw an F sub c. I associate the second name of centripetal force with the weight because it is the center directed force. So then we want the velocity. So then mg equals m. We're going to replace the a sub c with our formula, v squared over r. Mass divides out. And if we solve down for the velocity, that's going to be the square root of g times r. Don't memorize square root of g times r as some regular universal equation. It's not. In this case, it's the minimum velocity to be able to complete the circular path. So then if I want to calculate, that's going to be the square root of 9.8 meters per second squared multiplied by our 25 feet, converted into meters, which is 7.62 meters. So then that minimum velocity to be able to complete the path will be an 8.64 meters per second. Part C. Calculate the centripetal force acting on a 70 kilogram rider at the top and approximate the force acting at the bottom. If we want the net force acting on the rider at the top is going to be m times a. The only force acting on the rider at the top is mg, and that's equal to ma sub c. These two sides of the equation are equal, so the easiest way to get the value of the net force, which is the acceleration, is probably going to be the mg side, 70 kilograms times 9.8 meters per second squared, and that's going to give you your value at the top. At the bottom, we're going to have to do a little bit of approximating, because when we go net force is equal to mass times acceleration, we have the normal force minus mg is equal to ma, and this is going to be a centripetal acceleration. Mg, that's easy enough to get. Normal force, even though the arrows that I've drawn on the free body diagram above are reasonably the same length, your normal force, if you've ridden a roller coaster before, you know at the bottom you're more crushed. The force is going to be the strongest at that point, and the force is the strongest because now you've gone from the top of the hill down to the bottom of the hill. You've accelerated, you've picked up velocity. Your velocity at the bottom is the greatest. And if your velocity at the bottom is the greatest, then your centripetal acceleration at the bottom is the greatest. So we don't have an easy way to be able to calculate the normal force, but we can approximate, if we can approximate your velocity at the bottom. So if we're going to approximate the velocity at the bottom, well, what we know for our situation is that at the top, you were traveling 8.64 meters per second. At the top, you had potential energy and kinetic energy. At the bottom, that energy is going to be transformed into all kinetic energy. So then we're at the top here, and we're at the bottom here. If we use conservation of energy, recalling that from last year, or you could approximate this also using a motion equation, then we would go mgy plus 1/2 mv squared, that's at the top, equals 1/2 mv squared at the bottom. Your mass divides out, and we're going to get this final velocity squared. I'm going to multiply the whole equation by 2, equals 2gy plus the initial velocity squared, which is your motion equation, vf squared equals vi squared plus 2a delta y. So we can approximate what your velocity is at the bottom. This is going to be 2 times your negative 9.8 times the distance down. That's going to be the radius of the circle was 7.62 meters. So then we're going to be at 15.24 meters for that total vertical distance, plus vi squared. That vi is 8.64 meters per second, and that's going to be equal to vf squared. Now, as we solve this down, recognize that not only gravity is downward, but your 15.24 will be downward from the top, so that's going to be a negative. So then, plugging this into the calculator, I get vf squared is equal to 373.35, square root of that, 19.32 meters per second. So then we can calculate the centripetal force as m times a sub c, 70 kilograms, times v squared over r. That's a 19.32 meters per second quantity squared divided by the radius, which was 6.72 meters. And that's going to give us 3,428.92 newtons. So, the big thing to remember about centripetal force in objects in circular motion, F sub c is never drawn on the diagram. It's always going to be a second name. So then you will need to recognize when you have a motion that is a curved motion and you do that net force, you're going to have that A become an A sub C, and you're going to plug in a V squared over R. So you have to recognize those circular motions or those arcs of circles and bring that additional tool in. Ponder physics.